Hi guys, welcome to this presentation series on feature engineering for data science and machine learning. We have talked about few of the filter methods. In this video also, we'll talk about one of the filter methods called univariate feature selection. As you know, feature selection methods focus on understanding individual column and also providing descriptive statistics on each of the column. And thereby it allows us to understand the columns and the relations within the column or groupings or patterns within the column. And that's how we can decide which columns to keep and which columns to remove. And we have a reduced set of features for our machine learning modeling. In the previous videos, we talked about variances, how low variances can affect the model, machine learning models, and covariances, the idea of covariance and what is the geometric interpretation of covariance, then correlations and multicollinearity. We talked about correlations, the various types of correlation. We also discussed one of the methods for filter methods called information value. In this video, we'll talk about the univariate feature selection methods. The range of methods are typically hypothesis testing, and we'll cover three different hypothesis testing methods as part of univariate feature selection. Okay, so univariate feature selection methods are for evaluating the relevance of individual columns with respect to the target column. So that means we are going to be looking at whether the columns like X and Y, they have strong relation like X1, X2, X3, and whether they have strong association with Y column or not. So that's what is univariate feature selection. Univariate means single variable. So it involves evaluating the relevance of individual columns with respect to the target column. It also allows the ranking of the column in terms of significance, and it treats each of the column independently. That's quite obvious because we're going to do single column analysis. That means one column is being analyzed at a time. So is pretty much going to be independent, right? Each column is treated independently. And this approach is very useful when we deal with large number of columns. As we talked about it, it is about independence of each of the feature. And primarily, most of the methods used in univariate feature selections are statistical in nature, mostly hypothesis testing. I've listed few of them like t-test, ANOVA, f-test, mutual information, chi-square test. We'll be covering a few of them in our video. So what's the advantage of univariate feature selection? First of all, the analysis is done one column at a time independently. So it is quite efficient and computationally quite fast. And since we are able to do independently the analysis of each of the column, we can quickly come to some conclusion if certain columns are useful or not, and thereby it will help us with dimensionality reduction as well. But there are some limitations of this method. Firstly, the method is we are not treating the columns together. So that means if you have interactions, let's say, a couple of columns, when they interact together, they might be useful, right? So that's not something that we do in the univariate feature selection. Some more limitations, and in the process, since we are treating every column independently, we may end up discarding those features. If those features are combined, probably we get a better result. That's another limitation. And we consider all the features independently. That's another limitation in a way. So some of the methods that are used: ANOVA, chi-square, and t-test, and select, k-best, mutual information, and these are very popular univariate feature selection methods. A little bit of hypothesis testing as a recap here, although this is a statistical topic. We'll do a quick recap on hypothesis testing. So what is hypothesis testing? A series of methods. They are used to make inferences about a larger population by taking smaller sample. So the example would be, let's say you have a column and the column has 100,000 rows. We'll just pick a few samples out of it, let's say 50 or 100, and using that we can establish the notion about the larger population, let's say complete data set or complete domain. So that's the idea of hypothesis testing. It involves formulating some hypothesis. I mean, what is the meaning of hypothesis here? Let's say you have a column with some measurement, and these measurements are numeric. Let's say temperature measurement. So the hypothesis would be the average temperature is 31.5 degree centigrade. So that's the hypothesis. Okay, and then you go on collecting the data or sample data and conduct the statistical test, and after that we conclude whether 31.5 as a population parameter really holds true as the hypothesis or not. So we're going to have null hypothesis. So the meaning of null hypothesis is, let's say the population mean of something is 50, and that's called null hypothesis. For example, the temperature is 31.5 usually. And if that is given or that is understood, that is like acceptable, then we say that this is a null hypothesis. The counter hypothesis is, which is just the opposite of the null hypothesis. So we're going to say here the mean is not equal to 50. Let's see some examples of null hypothesis. Here, medical treatment, new drug has no effect on the patient recovery. So that's the null hypothesis. So the alternate would be, yes, the drug has some effect. It improves the patient condition. Educational intervention, let's say teaching method has a new teaching method, and the null hypothesis will be, well, this has no impact on the overall performance of the student. And the alternate hypothesis would be, yes, it does have some impact and it improves the performance of the students. Quality control in the manufacturing, let's say the mean product weight is something, some range. So that would be the null hypothesis. And the alternate would be just the opposite of that. That means the mean of that dimension is not in the range. Climate change, there is no significant change in the average global temperature. That's the null hypothesis. And the alternate would be just the opposite of that. Now, we're going to deal with few jargons here in the univariate feature selection: t-statistic, p-value, and critical value. What is t-statistics? So when you have sample data and then you provide the sample data to the statistical function, let's say ANOVA, chi-square, or any other statistical test, and the statistical test is going to give you an output called, some real number, and that's called t-statistic. For example, typically it's called test statistic, means the output from the statistical function. Now, along with the t-statistic, statistical functions also return a probability value. How probable is the sample mean that we have provided, for example, right? So it's going to return you something like 2% and 3% or whatever. It can be more also. Now, we'll see the rationale behind the t-statistic and p-value in terms of how do we use these two values to conclude or infer from the test or test results. Critical value is like a reference point, and using the critical value, we use t-statistic or a p-value to make the judgment. So let's take an example on this. Let's say we want to test the average height of certain population. Let's say your city is different from 65. So the null hypothesis is going to be 65 as the mean, and that's the null hypothesis. Alternate hypothesis is not 65, is different, is either less than 65 or more than 65. Now we set this significance level. That means we're going to say, this is very crucial to understand what is the meaning of significance level. Let's say the height here, the average height is, here given as 65 or 68 here, and standard deviation is 1.5, so 1 standard deviation. And this is 2 standard deviation, and this is 3 standard deviation on the higher side. Similarly, 1 standard deviation on the lower side, 2 standard deviation, and a 3 standard deviation. Empirically, what we say that is the range covered by 1 standard deviation is 68% of the population. Let's say you have a sample of 100. That means 68 of the 100 would be in this range of the height of 66 and 66.5 and 69.5. Similarly, 2 standard deviation, which is 95% here. So if you have a sample of 100 people, 95 of them would be in the range of 65 and 71. And likewise, the 3 standard deviation is almost close to 100%, slightly lesser, 99.7% here. So you're saying out of 100 people, 99.7 would be in this range here. So significance level is how confident we are with our null hypothesis, which is 68. And if we are really confident about this, we can say, okay, yeah, let's go ahead with the significance level of 95%. So if my new sample exhibits, um, a probability which is outside of 95% and quite regularly, then that would mean the mean of 68 is questionable. So that question that we do on the given null hypothesis is based on significance level. And this is actually, it depends on what kind of test we're doing, what domain it is, and how critical is the test. Typically for enterprise data like numeric data, banking, finance, and retail, we take about 95% as a level of significance. That means we are confident 95% that our sample mean or the population mean is true. Now, you leave 5% just as the chance of committing some error. It may be error, may not be error. Now, this is the crucial part. Now, if you have collected many samples and all of these samples fall within the 5% range, that means there is something wrong with the null hypothesis. We'll see in the examples like in t-test and ANOVA how we make use of the significance level. Now we carry out the test. Let's say we have a sample of 100 and we measure the heights and then we choose some statistical function. We provide all these heights of 100 people to the statistical function. Statistical function is going to return the t-statistic and the p-value. And based on the p-value here, and notice here the p-value is 0.03. And now you're going to compare this p-value with 0.05. As I mentioned, this 0.05 can be configurable. It can be 0.05, 0.01, depending on the domain. But for most of the banking, finance, and typical enterprise data, we use 0.05 as the reference. So if the probability value returned by the statistical function is lower than 0.05, then we reject the null hypothesis. That means there is something wrong with the null position. And then we say that the height of people is not 68 inches, something else. So this is all about hypothesis testing, and we will be using Python packages to carry out some of the univariate feature selection methods. The first feature selection method, univariate feature selection method that we will cover is t-test, but that will be in the next video. Thank you all. We'll see you in the next session.